Okay, we're going to go ahead and get started. Good afternoon, everyone. Welcome to the Florida Remediation Conference. You will get more official remarks and comments tomorrow at the opening session, but I would like to thank everyone here who's with us today, including all the golfers who are having a good time at the golf course. We will shift the order of presentations a little bit. Dr. Lakhwala will go first. Michael Scalzi will go next. Tommy Jordan third, and at the end we'll do Dr. Leslie Smith presentation. Every presenter has approximately 30 minutes. We decided that the presentation will be about 20-25 minutes, and then we'll take questions at the end of each session. There will be someone handing the microphone in the room, so if you have questions, please raise your hand and we'll give you the microphone. We can hear you, there's a good chance that we will hear you, but the reason we use microphone is we record all the sessions and it's better for the audio recording. Okay, let's go ahead and get started. The session is about remediation case studies. Our first speaker is Dr. Fayaz Lakhwala, Key Account Manager, Soil and Groundwater Remediation, Evonik. And Dr. Lakhwala will talk about evaluation and implementation of in situ solidification, in situ chemical oxidation at a dry cleaner vapor intrusion site.
Okay. Can everyone hear me in the back? Okay, good. All right. Well, thank you all, and good afternoon, and thanks for joining me in kicking off the Florida Remediation Conference 2022. Interestingly enough, I've been on about for 30 years on the conference circuit. Never had the chance to be the opening speaker, the first speaker in the conference, so this is exciting. I'm going to talk about two technologies, in situ chemical oxidation and in situ stabilization, and how you can combine those two, and present a case study at a site in Michigan where this technology was applied. Just a quick business update. We have been attending the conference for many years. Some of you may know us as Peroxichem over the years. Peroxichem was recently in 2022 acquired by Evonik. Evonik is a specialty chemicals company headquartered in Germany, about 30,000 employees. We operate in 27 different countries in 6 continents. Evonik, the Peroxichem soil and groundwater business was integrated into Evonik's active oxygens business in October of last year. And we are the largest manufacturers of hydrogen peroxide, persulfates, peracetic acid, and some of the other chemistries. Here is a quick update of our portfolio. You can see we not only make chemical oxidants, but we also provide remediation amendments for aerobic bioremediation, anaerobic bioremediation, metal stabilization. You'll also hear about NAPL stabilization. Mike Scalzi, who's going after me, will talk about the ISGS. So we have a wide variety of products in our portfolio. So the presentation outlines very straightforward. I will talk a little bit about ISCO, a little bit about ISS, and then how we can combine and use them synergistically, and then get into the case study for the can cleaners. So what is in situ stabilization? In situ stabilization is essentially a mixing process in which binders such as Portland cement, blast furnace slag, etc. are mixed into contaminated soils. And the objectives there are threefold. One is to reduce the hydraulic conductivity of the soil. Second, to increase the unconfined compressive strength of the soil, the UCS. And the third is to lower the contaminant flux and the leachable concentrations that emanate out from the contaminated soils. On the other hand, in situ chemical oxidation is a destructive technology. So what are oxidants? Oxidants are essentially reagents that take electrons from and/or oxidize the contaminants of interest. They're typically applied via injections through injection wells or direct push injections And the oxidants can also be applied using soil mixing technology. The objective there, again, is destruction. So you're trying to destroy the mass of the contaminants and subsequently reduce the leachate concentration, also reduce the vapor intrusion concerns, and also basically reduce the contaminant concentration in the soil. So over the last 20 years, closure sodium persulfate has been widely used as an oxidant. And the reason is because it is very versatile. It can be activated with the different mechanisms and produces a lot of different radicals, oxidative radicals as well as reductive radicals that can be useful in treating a wide range of contaminants. And one of the activation methods is alkaline activation method, where the pH is increased to about 10.5. And this process, or this activation method, goes hand in hand with the in situ stabilization, because a lot of the in situ stabilization reagents, like Portland cement, blast furnace slag, they are all alkaline in nature, and they activate the persulfate when they're mixed together. So here's a chart that shows all the different compounds that can be treated with activated persulfate. And you can see that some on the, oops, sorry, go back. I was trying to find the pointer. There's a pointer. Okay. Okay, so you, no. Okay, I'll continue on. So on the left-hand side, you can see the compounds that can be treated by oxidative pathways. These are typically your petroleum hydrocarbons and such. On the right-hand side, you'll see compounds that can be treated by a reductive pathway. These are typically your chlorinated compounds and pesticides. And in the middle, you see compounds that can be treated by both pathways. So depending on how you activate the persulfate, you can treat a variety of different contaminants. Okay. So the two technologies, when they're used separately, they have certain limitations. Especially now we are talking about sites that are heavily contaminated. So at heavily contaminated sites, usually multiple applications of chemical oxidation is required. Also, at heavily contaminated sites, most often the geology is very heterogeneous. So there's a lot of clays and silts. And that means that contaminants are very much sorbed to the soil. And to treat those contaminants is also very challenging, and it requires multiple applications. So those are the kind of limitations of using ISCO alone. As far as the ISS goes, the contamination is not destroyed. It is basically left in place, which is a long-term liability. And in addition, the use of binders, etc., that causes a lot of soil bulking. So essentially, every ISS project also is a soil disposal project, if you are not aware of it. Because of the bulking of the soils, a lot of the soil has to be taken off-site after the treatment is done. So what happens when we combine the two technologies together? So this was in 2016, Srivastava et al., who is now with Burns and McDonnell. He did a lot of the initial work in the lab to demonstrate that combining the two technologies has a lot of merits. And this slide over here presents some of the data from his study. But essentially, what happens is that the more soluble compounds are first preferentially degraded, and the less soluble or less available contaminants are basically entrapped and stabilized in the ISS matrix. He also demonstrated that adding small amounts of persulfate to the ISS mix reduces the total amount of amendments needed, or the reagents needed, and hence there's less bulking of the soil. So the chart on top, you can see there is the data for BTEX, naphthalene, and 17 pHs. The blue line is for BTEX, the red line is for naphthalene, and the gray line is for the pHs. The solid lines are the ones where persulfate was added to the mix. The dotted lines at the bottom are where only ISS was used. The chart demonstrates the percentage reduction in the contaminant concentrations in the two cases. So it's obvious that in the case where persulfate was added, you get some destruction of the contaminants, where the bottom dotted lines show no destruction because it was only ISS component over there. And the chart below shows the reduction in the leachate concentration, which is, again, expected, because if you destroyed some of the contaminants, then you're going to leach even less contaminants as a result. He also demonstrated in the study that adding small amounts of persulfate also decreases the hydraulic conductivity. That can be seen in the chart on the left. By adding about 1 to 1.5% of sodium persulfate, you can get one order of magnitude lower reduction in the hydraulic conductivity. And they also demonstrated on the right that by adding small amounts of persulfate, the unconfined compressive strength of the soil also increases. So if you add about 2% persulfate, it increases the unconfined compressive strength. Okay, so that was kind of the background on what ISCO is, what ISS is, and what are the benefits of combining the two technologies together. So with that, I want to get into the case study of this dry cleaner site in Michigan. It's a Kent Cleaner site. The dry cleaner operated for about 17 years. It's an orphan site now. The state of Michigan Environment, Great Lakes, and Energy basically took the lead on this one. It's a 0.4-acre site in a very tight residential setting. The soil is significantly impacted with PCE. I'll show you some data on that. And essentially clay soils with very thin sand lenses were present at the site. So this chart shows you all the concentrations, if you can read that from back there, I'll tell you the pink one in the middle is 1 million microgram per kilogram of PCE. The dark orange is between 100,000 to 1 million micrograms per kilogram of PCE, and then the yellow is 10 to 100,000, and green is 1,000 to 10,000 micrograms per kilogram of PCE. So you can see that this is really, really heavily impacted, significantly impacted with PCE. The groundwater is about 27 to 30 feet below ground surface, so this was mostly a unsaturated soil contamination problem that posed a significant vapor intrusion problem. An off-site investigation was done for VI in 2017 and 2018, and they found that there was significant concentrations detected above standards in some of the residential houses at the bottom. And then one of the houses, as you can see there, at 527 South Dunlap, they had to install an SSDS system to mitigate the vapor intrusion. So the purpose of the remediation was essentially to reduce the mass of CVCs in soil and lessen the potential for vapor intrusion, and also to reduce the potential for leaching into groundwater, underlying groundwater of the PCE. The chart on the right, or the figure on the right, shows you where the mass of the contamination was and the treatment area. The conventional treatment technologies pose several challenges, like excavation in the neighborhood, in the area, and basically trucking of contaminated soils was not going to be easy. So there was a lot of intrusiveness that was involved with using conventional technologies. So the idea was to then go with a combination of ISCO and ISS. So with that, we started off with doing bench studies in early 2019. Soil samples were collected from the site, and several mixtures of sodium persulfate and Portland cement were experimented, and certain goals were set in place. Goals for hydraulic conductivity, for compressive strength, for leachability, and those studies were conducted, and from these bench studies results, the full-scale application was designed. So for the full-scale application, which happened in fall of 2019, 2% sodium persulfate was used in the hotspot area, very high concentrations, and 1% sodium persulfate by weight was used in the remaining of the area. and then 4% Portland cement was used throughout the entire area. So this was really the mix that was implemented with the soil mixing. And the delivery was done using Lang Tool Company's dual axis blender. So that's, and there is a video here. I don't know if the video can be played. Is it possible to play the video? If you click on, yeah, there you go. Okay, so short video, but that just shows you the dual axis blender, how the rotation is happening and how the mixing is happening. All right, okay. So site preparation, the whole area was divided into treatment cells, 10-foot by 15-foot cells. An onboard GPS system actually was used that gave the operator the precise location and the depth. And also the system was in place to measure the exact amount of the Portland cement and the persulfate that was being injected. Delivery and mixing was done in the same tooling, so it wasn't separate. Everything was done simultaneously. Treatment was done in 2 lifts, 2 tiers. There was a lower tier that was treated first from 7 to 23 feet below ground surface, and then the upper tier was treated later on. And the whole process basically made sure that there was enhanced contact between the contaminated soil and the reagents that were being mixed. And about 12,400 cubic yards of soil was treated over a 28-day period. So that's some pictures of the 2 mixing, the lower tier mixing and the upper tier mixing. And post-treatment sampling was done, and about 36 discrete samples were collected from 12 different locations and analyzed for PCE, analyzed for UCS, the unconfined compressive strength, hydraulic conductivity, and also underlying groundwater samples were collected to see what the effect was on the groundwater concentrations. So here's the data on the soil. The average PC concentration in the area, in the source area, was about 5 million micrograms per kilogram prior to the mixing. And after the first day, the concentrations were down to 1,600,000 micrograms per kilogram. After the treatment, we were taking samples and monitoring. The treatment continued, or the destruction continued for about 45 days, even after the mixing was done. And then the final PCE concentration was about 60,000 micrograms per kilogram. An attempt was made to calculate how much mass was destroyed by using the soil samples and taking a cross sections. So the total PCE mass was reduced from about 4,400 pounds to 248 pounds. That was estimated, about 94% reduction in the total CVOC's mass. The UCS, the unconfined compressive strength, ranged in the 25 to 50 PSI range after 60 days, and the hydraulic conductivity was reduced to less than 10 to the minus 6 centimeters per second. And here's some information about our data on groundwater. The groundwater concentrations to begin with were 600 micrograms per liter of PCE, and were reduced to about 5 micrograms per liter after 1 year of monitoring. Again, the groundwater was much lower. It's about 27 to 30 feet, and all the mixing was done in the 23, 24 feet elevation level or depth level. And you can see there were 3 monitoring wells, and here's the data from them. Monitoring well 1, primarily, it was cis-DCE. Monitoring well number 2 was primarily PCE, which is the red bar. And then the monitoring well number 4 was a mixture of PCE and cis-DCE. In all, we got about 40 to 90%, 99% reduction in PCE in these wells, and about 84 to 99% reduction in cis-DCE in these monitoring wells. Okay, so in summary, ISCO-ISS successfully met the remediation goals that were set for the site, that is CVOC mass reduction, VI reduction, reduction in leachability, and the UCS, unconfined compressive strength metrics. The CVOC's destruction was observed for 45 to 60 days. So the message there is that the way it was designed, the ISS component was delayed. Usually when ISS is done by itself, within 28 days, you want to get your unconfined strength, you want your hydraulic conductivity reduced within 28 days. But in this particular case, the way we designed it, we had to extend that setting period of ISS so that the oxidation reaction can continue and destroy the contaminants. So that's a key component of combining the two and using the two in a beneficial way. Again, treated about 12,400 cubic yards of soil in 28 days. Remediation was completed without significant disruption to the neighboring community and residences. It was a sustainable remediation because we did not end up excavating and sending soil off-site, and very less amount of Portland cement was used. And it was a cost-effective treatment at $133 per ton. And with that, I've got 10 minutes left for question and answers. Thank you. Nope.
Now it's excellent. Excellent. Depth of water was 27 feet below land surface, but it seemed in your photograph that there was liquid in the open pit.
Yeah.
And my question was that the persulfate mixture being added in there? And then with that, you indicated that you were adding certain amounts of persulfate in different areas. I'm assuming that, can you explain how you might add different amounts in that open pit when the entire thing was full of liquid?
Yes, so a good observation on, you saw in some of the photos there that we were dealing with saturated soils. So yes, to make contact and for all the contaminants to desorb, the oxidation reactions occur in the aqueous phase. So you have to basically add copious amount of water to get that desorption to occur in the aqueous phase, and that's where the oxidation reactions occur. So you're right, the amount of water that was added was 125% of the water holding capacity, basically saturating the soils.
Thank you, Dr. Fayaz, presentation. I have a short question. Do you have any number for effective depths and radiation of each injection?
I'm sorry, there's a lot of echo. I'm not following your question.
Do you have any any number for average effective depths and radiation for each injection? How long the material can diffuse in the soil when you inject them?
So this was not an injection process, right? So this was a mixing process. So as the auger is moving down and up, at the same time, we are simultaneously pumping in the solution of Portland cement and persulfate.
So they will diffuse inside the soil?
Yes, so we are mixing it with the soil as the augers are rotating.
So you have several spots inside the soil, like you pre-select different sites for mixing?
So there were different ratios. So in the source area, we were using 2% persulfate and 4% Portland cement. So that mixture was different. And as you moved outside from the source area, we were using less persulfate and Portland cement.
But so, do you need maybe the soil characterization, right? We have to know the properties of soil before any injection, right? It will add to the cost or not?
Again, I'm not following your question. Sorry, there's so much echo.
So I mean, before any mixing, so for each point of the soil, laminated soil, we need weight of the soil, right?
You come up here, we can talk. Okay.
I think what he's asking is, how did you choose the points at which you were going to apply the treatment? Like the location?
The location. Okay, so that was based on the soil investigation that was done earlier on. That, the map that I showed, on the basis of which we laid out all the injection or the points, the treatment points. So the investigation was done. It was mapped out where the concentrations were horizontally as well as vertically. And that's where we went in and put all the mixing locations.
I think we have time for one more question. And just a side comment, the great thing about these conferences is that whatever cannot be discussed or answered here, we still have receptions, networking, and please get together and continue the discussion.
So one last question. What about production of daughter products, vinyl chloride, for example?
I can't follow the question.
Production of vinyl chloride. Did you get vinyl chloride?
Production of vinyl chloride? No. In the oxidative pathways, this is not a reductive pathway, right? So oxidation pathways don't generate daughter products. You probably produce some intermediates, but you don't generate vinyl chloride, as you would expect in a reductive pathway, a bioremediation pathway. So no vinyl chloride was.
Thank you.
Okay.
Thank you very much.
Okay, thank you.